In our last video, we will take a look at how to extend the linear regression model using multiple regression. So in multiple regression, we add more terms to the linear regression model. So rather than writing our response variable y is equal to beta 0 plus beta 1 x and then stopping, we'll continue to add additional explanatory variables to our model. So let's say we have up to p possible explanatory variables. Then we write y as a function of some intercept beta 0 plus beta 1 x1 plus beta 2 x2 all the way up to beta p xp. So essentially, we're adding more terms to the model we're already familiar with. Why might you want to use a multiple regression model? Well, being able to model multiple explanatory variables at the same time is incredibly powerful. Instead of looking at how each variable performs individually, we can take a look at the overall success of a model together. Not only that, but we can add more powerful terms. We can add things like squared terms to the model. We can add transformations like a natural log of x. All that we need to be able to do is write our model like this. So as long as we can write it as a coefficient times a variable, we can take different functions of those variables and still incorporate them into our model. So we'll take a look at an example data set from the Lock5 data library called the Stat Grades dataset. So this contains exam scores for a sample of students who completed a statistics course at a large northeastern university in the US. So our data set contains information on the first exam, exam 1, second exam, and the final. Now let's say we want to be able to predict how a student would perform or how they would score on the final exam based on their previous 2 exams. So looking at the first exam on the x-axis, there is definitely a linear trend. So students who score higher on the first exam tended to score higher on the final exam. The correlation between these two is pretty strong, about 0.7. The same is true for the second exam. Students who tended to perform better on the final exam as well. However, the correlation is not as strong for the second exam as it is for the first. So the first exam might be a better indicator or a better predictor. Now let's say we want to incorporate both exams into the same model. So our multiple linear regression model might look like this. Y is equal to beta 0 plus beta 1 times x1 plus beta 2 times x2. So x1 is the score for student I on exam 1, x2I is the score on exam 2 for student I. In order to fit this multiple regression model, we'll just use a plus sign within our linear model function to indicate adding more explanatory variables. So our final exam score is a function of, or depends on, with that tilde, exam 1 plus exam 2. Now, looking at our model coefficients, we can write the model like this. Our predicted final exam score, y hat, is 30.895 plus 0.446 times x1 plus 0.221 times x2. So let's find the predicted final exam score and residual for student number 1. So student number 1 scored a 91 on the first exam, an 86 on the second exam, and a 90 on the final exam. We would then predict, using this model, plugging 91 in here, 86 in here, we would predict that they would score about a 90.57 on the final exam. This student actually scored a 90% on the final exam, so came very close to their predicted score. The residual was about 0.57 for this individual student. Taking a deeper look at those model coefficients can be done in 2 ways. It can be done using a hypothesis test or using a confidence interval. So let's start with the summary output and take a look at a hypothesis test. So there are now 3 hypothesis tests that are being done, one for the intercept, one for the slope of the first input variable, the first exam, one for the second exam. So it looks like the intercept is significantly different from 0. There's strong evidence that beta 0 should not be 0. There's also strong evidence that beta 1, the effect of exam 1, should not be 0. However, there isn't strong evidence that the effect of exam 2 is non-zero, which is kind of interesting at first. Looking at the output, it looks like this model's explaining about 53% of the variability in final exam scores. We can also use a function called confint to get confidence intervals for the coefficients in the model. So let's focus in and interpret the confidence intervals for beta 1 and beta 2. So the confidence interval for the effect of exam 1 is right here, goes from about 0.12 to about 0.77. So we're about 95% confident that a 1 unit increase in a student's score on exam 1 will increase the final exam score by between 0.1 and 0.77 points. Look at exam 2. We're 95% confident that a 1 unit increase on a student's score on exam 2 will increase the final exam score between negative 0.13 and positive 0.57 points. It's kind of interesting. There is actually a 0 inside this confidence interval. So it's possible that exam 2 has no effect, according to this analysis. But looking at the plot that we had generated previously of exam 2 against the final exam scores, that doesn't really seem to make a lot of sense. It looks like there is a relationship between exam 2 and the final exam. The problem here, or what's happening, is that exam 1 and exam 2 themselves are highly correlated. So there's an 84% correlation between scores on exam 1 and scores on exam 2. So what happens in multiple regression is that when there's a strong correlation or a strong relationship between 2 predictor variables, one tends to overwhelm or dominate the other, and that's exactly what has happened here. Exam 1 is a little better correlated with final exam scores than exam 2, so all of that information essentially gets lumped into exam 1. So it's important that the variables in a multiple linear regression model are relatively uncorrelated, or as uncorrelated as they can reasonably be. Now, because we have multiple variables in this data, we need a way to assess the overall effectiveness of the multiple regression model, and we actually do that using a form of analysis of variance, or ANOVA. So here's the null and alternative hypothesis that is used in this particular ANOVA model. Our null hypothesis is that the model is not a good fit for the data. The alternative is that the model is a good fit. So what ends up happening is that if we have a small p-value for this ANOVA model, then we've got some strong evidence that this model may fit the data or may explain what is happening. Where we find that out, or where we get that information, is down in the very last column of the last row of the summary output. We look at the F statistic and the p-value. So the p-value here is quite small, 2.5 times 10 to the negative 8th. So there's some pretty compelling evidence to suggest that yes, we are able to explain quite a bit of the variation in a student's final exam score using their 2 midterm exams. Now in multiple regression, we still have this coefficient of determination, or this R-squared measurement, but it's now measuring something a little bit different. In linear regression, R-squared measured the proportion of variability in the response variable that can be explained using the linear model. It does this by squaring the correlation between the explanatory variable x and the response variable y. However, in a multiple regression setting, we have more than one explanatory variables. So, what do? Well, instead of focusing on the relationship between a single explanatory variable and x, what we do is take the correlation, or we find the correlation between the predicted values y hat and the observed values y, and then square that to measure our determination. There is a downside to this approach. No matter what, whenever we add a new explanatory variable to our multiple linear regression model, even if it doesn't provide much useful information, R squared will still increase. So when you're in a situation where you want to select or perhaps choose the best multiple linear regression model, what would we do? Well, simple models are good for a lot of reasons, primarily interpretability. It's easier to interpret and work with a simpler model. So there's actually a second R squared calculation that we can look at called the adjusted R squared. This takes the original R squared value and shifts it downward based on the number of observations in the sample and the number of variables in the model. So depending on what your goal is, you might choose one R squared over the other. Now, most of the time in this class, we're going to be trying to explain variability in our model. So we'll use the multiple R squared. However, if your goal is to choose the best model, you should be using adjusted R squared instead. So how much of the variation in final exam scores are we able to explain using this model? It looks like we're explaining about 52 to 53% of a student's final exam just based on these two midterm exams. So let's say we want to predict the final exam score for student 2. In order to find this prediction, we could certainly plug the numbers directly into the multiple linear regression model. So if we do that, we get a prediction of 91.24. There's actually a second way that we can do this. We might also want to find confidence intervals for the final exam score. So maybe this student will study a lot more, do better than expected. Maybe the student has a lot of final exams on the same day and does a bit worse than expected. So we might want a range for what a student's performance would look like. We actually have our choice between two confidence intervals, and it depends on what we're precisely trying to find. So we can calculate either a confidence interval, which just gives an interval for the mean value for all members of the population at a particular combination or level of X. Or we could find a prediction interval. So what the prediction interval does is create a range of values where we would expect a new observation to fall. So where are we going to expect that new observation to end up? Prediction intervals are always wider than confidence intervals. That's because prediction intervals are for a single value, and single values tend to vary much more than means do. So in order to do this calculation, we first need to create a new data set. Here I'll call this new X. This new data set is going to contain the exam 1 score, the exam 2 score, and it happens to contain the final exam score. It should not need to in order to make this prediction. We'll use the predict function next. So we'll write predict, we'll input our model. Our new data is new X. We can ask for either a confidence interval or a prediction interval. And here I've chosen to calculate 95% intervals. So we are 95% confident that the population mean final exam score for all students with these characteristics is between 88.66 and, apologies for the typo, this should say 93.83. So that's our confidence interval. For our prediction interval, we're 95% confident that a new observation, so a new student with these characteristics, should score between 78 and 104 on their final exam. Now, what if we want to do something a little different? What if we want to tell or investigate whether the relationship between two numerical variables changes depending on some categorical variable? Well, a simple way to do this is to fit separate linear models for each level of the categorical variable. So, for example, does the relationship between sales price of a home and state change depending on the state? Well, here's the overall linear regression model. It doesn't appear to fit the data very well. However, what if we split the data up into 4 different states? Well, there's a couple things to take away. First, New Jersey in the upper right has much less variability in home price than, say, California on the upper left. There's a lot more variation for home prices in California. The same is true with Pennsylvania having a very small variation and New York having a very, well, kind of a medium variation. So there's some differences in the variability. There are also some clear differences in the slopes of these linear models. The slope for New Jersey is not as strong as the slope for California or New York. So that is it for multiple regression. You'll get some more practice with these on some homeworks and practice quizzes. Have a wonderful day.